It all started with the realization by scientists like James Prescott Joule that there was a close relationship, if not an equivalence, between mechanical work and heat. To demonstrate this equivalence, Joule built the machine shown in this drawing, published by the Harper's New Monthly magazine in 1869. To help you follow Joule's argument, let me describe the machine he came up with. One part of this machine is a paddle mounted on a wicket, which can rotate inside a cylindrical water tank. A second part of the machine is a string attached at one end to a weight and at the other end to the wicket. The string, threaded through a pulley, is wound up on the wicket using an appropriately affixed crank. As the crank is turned and the wicket paddle rotates in one direction, the weight is raised to a height h, measured by a ruler. He waited a little time to allow his machine to reach thermal equilibrium, that is, he waited until the temperature of the water was constant and the same as the temperature outside the water tank. He then released the crank and allowed the wicket to quickly rotate, unwinding the string under the action of the weight. When the weight reached the ground and the paddle stopped rotating, he measured the change in the temperature of the water and the change in the height of the weight. He observed that doubling the weight or doubling the initial height of the weight would result in twice as large a temperature change. From these experiments, he concluded that the gravitational work of the weight, mass times acceleration of gravity times height, was transformed into the heating of the water through this process. It is possible to quantify this observation, that is, to express what was observed and measured using an equation. Joule considered that any system in a state of equilibrium has well-defined properties. By state of equilibrium, we imply that the properties of the system do not change with time if the system is left to itself. The particular property of the system associated with the sum of the potential and kinetic energies of all atoms, ions, and/or molecules in a system, he called the internal energy, or in short, the energy. He denoted this property by the symbol U. As a result of the process, symbolically expressed as delta U, equal to the sum of the work W and the heat Q exchanged between system and surroundings. This equation is obviously now known as the first law of thermodynamics. You can see in the case of Joule's machine that the first law makes sense. Mechanical work of the weight is equivalent to the mechanical work of the paddle, which is equivalent to the heat released by friction between the paddle and the water as the paddle rotates. The latter leads to an increase in the temperature of the water, which is equivalent to the increase in the kinetic energy of the water molecules, hence to an increase in the internal energy of the water. The first law makes sense, but it cannot be demonstrated from first principles. At least nobody has been able to prove the first law. Many have tried to show that it does not work in specific situations, and all have failed. This is the strength of the first law. Since it was formulated, nobody has ever been able to show that it does not work. The same will be said about the other laws of thermodynamics. Let us look at some properties of the internal energy, or the energy U. We know from the kinetic theory of gases that the energy U depends on the temperature. We also know that for non-ideal gases, for liquids and solids, that the strength of the intermolecular interactions change when the average distance between the molecules in a system change. So the energy would in this case depend on the volume or the pressure in the system. Obviously, the internal energy is the sum of the kinetic and potential energies of the particles contained in a system. So U is directly proportional to the number of moles N of substance in that system. Because of Joule's contribution to this field, his name is now used for the unit of energy. When a system is constituted by n moles of a pure substance, it makes sense to define an energy per mole, or a molar energy. which we write symbolically as U sub m, with units of joule per mole. In earlier chapters, we indicated that the energy U is extensive, and the molar energy U sub m is intensive. Hopefully, the interpretation of energy as the sum of the kinetic and potential energies of the constituent atoms, ions, or molecules helps make sense of why the energy is extensive, i.e., it is directly proportional to the size of the system. It is important to remember that the internal energy of a system cannot be actually calculated. However, this is not important because what we are interested in is the change in energy of the system as a result of the process, as is indicated by the first law.